Okay, before we begin, part of our beginning is just kind of talking about the names of these polygons, because on the EOC, if you encounter a question that says something about, let's say, a nonagon, you can't raise your hand and ask your proctor that. We can't help you. Okay, so you have to know the names of these polygons. So if there's any of those that you don't know the name for, when I tell you the name for it, you probably want to write it down. Of course, a three-sided figure you know as a triangle. Four sides.
Square.
Quadrilateral. Five sides. Pentagon. Six sides. Ouch. Hexagon. Come on. Seven sides. Heptagon. Very good. Number 8. Octagon. 9 sides. Nonagon. 10 sides. Decagon. 12 sides. Dodecagon. Very rarely, occasionally, sometimes you see the name for an 11-sided figure. It is undecagon. It's if you heard me say undecagon, that's what it sounds like, and that's how you would spell it. I like pronouncing it undecagon because it makes more sense that way. Okay, good? Fine? Lovely. So I shared with my classes today some bad news that I got about reference sheets. You already know the really bad news that this is not the reference sheet that you get to use on next week's EOC. The worst news is that they don't give you a paper reference sheet like you've had in the past. She texted me back and said, no, I misunderstood you. Yeah. All right, yeah. So you don't get a paper reference sheet. The only reference sheet that you have access to is the one that you click the button on the screen and then you get the pull down for the reference sheet. So let me give you, if I'm thinking about it, the reference sheet that you'll have next week. If you're on my roster, I'm not going to give you one because I already gave you one today. But if you're not mine, then I'm giving you one, just in case your teacher hasn't given you one. So that as we're going through, if there's any formula that I mentioned that is on the old reference sheet, that isn't on this reference sheet, that maybe you want to be reminded to study over the weekend, maybe you want to write it down. Okay? Anything that I give you here is yours to keep. Right? So, something that isn't necessarily a formula, but is a really wonderful tidbit of information, and I gave this to you on that sheet that you received, that the exterior angles of any polygon, no matter how many sides it has, the exterior angles will always add up to 360. A couple of formulas that you may or may not have committed to memory that maybe you want to add to your copy of the reference sheet so that you have something to study from over the weekend. The sum of the interior angles. That's n minus 2 times 180. And if memorizing formulas doesn't really work for you, then let me show you once again, for those of you that are already mine, you've seen this once already, let me show you why this formula is what it is. For example, if I take a polygon, let's say I have a hexagon. And you don't have to copy this down. If it makes you happy, go ahead. But I'm just trying to show you why the formula is what it is, so that if this formula falls out of your head over the weekend and Monday morning you see a question like it, maybe you can remember why the formula is what it is. If I go from one vertex and make as many diagonals as I can, think about what a diagonal is. A diagonal is a segment connecting non-consecutive vertices. So any vertex has 2 vertices adjacent to it. So that takes away 2 sides. Notice how many triangles there are here. I have 1, 2, 3, 4 Notice that the number of triangles I have in here is 2 less than how many sides this figure has. And of course, you know that the sum of the angles of any triangle add up to 180. So that's why I take the number of sides, I subtract 2 from it, and then I multiply that times 180. That's this formula right here. Okay? So if I know what the angles are supposed to add up to, and I know that the figure is a regular polygon, that means all of the angles are congruent, does it make sense? I would just take that and divide it by however many sides there are, and that's going to tell me the measure of each angle. So once again, another formula. The measure of each interior angle in a regular polygon is n minus 2 times 180 divided by the number of sides. So let's apply that in the next couple of problems on the polygons and quadrilaterals sheet that I've given you. So you're still getting from up here what you need, so I'll pause for you. Is it warm in here or is it just me?
It's pretty warm.
Okay, we got from the screen what we need? Good. Great. Lovely. Onward. Okay, so in the question on the left, I'm asking for the measure of each angle, interior angle. Just kind of so you know, unless they specify exterior angle, assume they mean interior. Okay, so that's this formula. How many sides did I tell you a nonagon had?
9.
So you're taking 9 and plugging it in for n. So 9 minus 2 is 7 times 180 divided by 9. I see a lot of students, and the rest is just calculator. I see a lot of students that will take the 9 and plug it in here and then think they have to distribute the 180. Don't do that. You're making your life more difficult than it has to be. These are just numbers. Use order of operations. That means you do what's inside the parentheses first, and then you multiply it times the 180. So the measure of each angle of a regular nonagon is 140. In order to find the measure of angle y in that polygon, what very convenient piece of information would we need to know? How many degrees it all has to add up to. So that, once again, we find by using, whoops, I went in the wrong direction. Once again, we use this formula in order to find out what those angles are all supposed to add up to. So there's 1, 2, 3, 4, 5. So 5 minus 2 times 180 means that all of these angles are supposed to add up to 540. So the next thing that most students would probably do looking at this problem is, well, I have a bunch of angles, let me add them all up. So 110 plus 120 plus 150. What mistake do you think some people might be inclined to make? Yeah, there's no number at the 90 degrees, so it'd be a common mistake for students to not count the 90. You have to realize it's there. Even though you don't see a number, you know that the number is 90. And then you subtract that. From 540, and you get that y is 70. Do I not look miserable enough up here? Okay, just stop. Yes.
Are there going to be like the zero questions on the...
I have no idea what's going to be on the EOC. I mean, if you recall, guys, when you went and you took the practice EOC, there were some questions on there that were as easy as, like I was pointing this out to an earlier class. So I know some students are like, how can we take a math test with no calculator? That question up there on the practice test, when you had a diagram like that and they asked you to click on a pair of vertical angles. You don't need a calculator for that. You just click on an angle like 1, click on an angle like 4, and that would be it. I think that's a ridiculously easy question. But if it was on the practice test, I would say it's feasible for it to be on the real thing. You never know. Okay? We good on this screen? Onward. Okay, so that's basically all I need to say about polygons. Hereafter, we're talking about parallelograms and other kinds of quadrilaterals. A couple of things about a parallelogram. If you have a question and they tell you that it's a parallelogram, right out of the gate, you know a whole lot of stuff. First of all, what does it mean for a quadrilateral to be a parallelogram?
Parallel line.
Right, 2 pairs of opposite parallel sides. So you definitely know that right out of the gate. You also have that opposite sides are congruent. You have that opposite angles are congruent. You have that consecutive angles, and don't let that word trip you up. Consecutive just means one right after the other, one right next to the other. Consecutive angles are supplementary. And diagonals bisect each other. Please be really careful. Oh, stop. They bisect each other. Please be very careful about misunderstanding what that means. Diagonals bisecting each other does not mean that the diagonals are congruent. It means that the diagonals are cutting each other into congruent pieces. Okay, be very careful with that. Okay, so a couple of examples using properties of parallelograms. How can I solve for x here? That's how I could solve for y, absolutely.
Oh, I thought it was like that one you showed me in class.
And that one, the opposite sides had different variables, and there was no other way to go around it. In this one, they were particularly nice. Opposite sides have the same variable. Okay, so here I solve for y, and I get y equals 7. Done deal. Unless the problem is asking me to find the length of a side. Read the question. I can't stress to you enough. When we the geometry teachers do our data analysis of how students do on tests, it's really, really distressing that the math scores kind of correlate with students' reading scores. In other words, if a student is a struggling reader, it's kind of anticipated that they may struggle on a math test. Not because they don't get the math, but because either they didn't read the question or they misread the question. So take your time and read the questions especially carefully, especially if you know that reading is kind of a troublesome thing for you. Okay, solving for x, same idea. 5x minus 1 equals 3x plus 1. So 2x is 2 and x is 1. Easy peasy. Now in the angles problem next to it, the opposite angles have the same variable. So that works out nicely. But just for kicks and giggles of it, suppose that this was an x angle and this was a y angle. And this was an x angle and this was a y angle. You probably wouldn't want to set up an equation with x's and y's in it unless you absolutely have to. But if I had, again, let me clarify what I mean. If the x's weren't opposite angles, but they were angles like here and here, you could, yes.
Isn't it negative side?
I subtract y from both sides, I get 1y on this side. I add 9 to both sides, I get 9, positive 9 minus 2. So the point that I'm trying to get across over here, ladies and gentlemen, is if I have these two angles in terms of x, don't lose track of the fact that consecutive angles are supplementary. So it's not as pretty an equation as this equals that, but it's still doable. Okay, so in this one, like I said, these opposite angles are congruent. And all I have to do is subtract 3x from both sides, and 26 equals x. And then for y, same idea. Subtract the 5.
Please excuse this interruption. Mackenzie Clark, please report to Building 3, Room 226 at this time. Mackenzie Clark, Building 3, Room 226 at this time. Thank you.
I subtract the 5y from both sides, I get 2y. Add 1 to both sides, I get 22. And y is 11. Got from the screen what we need? Not yet. Alright. On to special parallelograms. These are quadrilaterals that have all of the characteristics of a parallelogram, which are what we just discussed on the previous screen, and then on top of that, there's extra stuff about them. And I'm giving you the properties without actually talking about the definition, and maybe that's not the best idea, so let's make sure that we talk about the definition. What does it... I already have to talk over that. What does it mean for a parallelogram to be a rhombus? What's the definition of a rhombus? That's what I'm trying to get at.
Four-sided figure.
Well, that's a parallelogram. What makes a parallelogram a rhombus? All 4 sides are congruent. If that's not something that you knew, you probably want to write that down. Okay? A rhombus has 4 congruent sides. What makes a parallelogram a rectangle? What separates a parallelogram from a rectangle? What does a rectangle have that a parallelogram doesn't? That's a parallelogram.
All
90-degree angles, yes. Okay? And then a square is just something that, exactly, everything is congruent. The sides are all congruent, the angles are all congruent. All right, so now talking about the properties of these things, if a parallelogram is a rhombus, then the diagonals are perpendicular. And if you're looking at that symbol and the word perpendicular doesn't automatically jump to your brain, then that's something you want to write down. Because again, if you see that symbol next week and you don't know what it means, you can't raise your hand and ask us to clarify it for you. We can't. And the diagonals bisect opposite angles. If a parallelogram is a rectangle, then the diagonals are congruent. Okay, so what these properties allow for us is if I know that something is a parallelogram and they tell me that the diagonals are congruent, I can use that to conclude that it's a rectangle. If I have a parallelogram and its diagonals are perpendicular, I can use that to conclude that that parallelogram is also a rhombus. So let's apply these properties. In number 1, and again, notice all the way down, all of these sentences start with a parallelogram. Okay, so these are all parallelograms, but are they more than that? So in number 1, I have a parallelogram with perpendicular diagonals and angle measures of 45, 135, 45, and 135. Can it be a rhombus? Can it be a rhombus?
Yeah.
Yes. Can it be a rectangle? No. So if it can't be a rectangle, then it definitely can't be a square. Okay, so number 1 is a rhombus. Number 2, parallelogram has perpendicular and congruent diagonals. So let's go down the list. Can it be a rhombus?
No.
Look back at the diagonals are perpendicular in a rhombus. So yes, it can be a rhombus. Can it be a rectangle?
No.
Yes. diagonals of a rectangle are congruent. And then by default, if it's a rhombus and a rectangle, then it's also going to be a square. Parallelogram has perpendicular diagonals and angle measures that are all 90 degrees. Say it again. It's a square. And since it's a square, we also know it's a rhombus and a rectangle, so let's just, for the purposes of your studying, write all three down. If a parallelogram has congruent diagonals, what am I guaranteed that it'll be? Rhombus does not have congruent diagonals. A rectangle. Is it a rhombus? No. A square has to be both. Good question. Okay, here. A couple of other kinds of quadrilaterals, kites, and trapezoid. A couple of things about a trapezoid. Looking at the figure all the way on the right here. Because this trapezoid is an isosceles trapezoid, I know that its base angles will be congruent. Please understand that a trapezoid has two pairs of base angles. These are base angles, angles 1 and 2, and then 110 and the angle next to it are also base angles. Because this particular trapezoid is an isosceles trapezoid, I know that the base angles are congruent. So once I figure out what angle 2 is, I'll know what angle 1 is. They're the same. What I also know in any trapezoid is that the 110 and the 2 that I've circled have to add up to 180. So the measure of angle 2 is 70, and as I said, once you know angle 2, you know angle 1. I do, however, want to add an example to this because a lot of times students see this and then want to pretend that every trapezoid is an isosceles trapezoid. Just like with the special right triangles, once you saw a special right triangle, you wanted to treat every triangle on Earth as if it was a 30, 60, 90. And you can't do that. Okay, sometimes there's just Joe Schmo trapezoids. So for example, if I have this Joe Schmo trapezoid, and I know that this is 75, and that this is 140. How do I go about finding x and finding y?
The 140 and the x is.
The 140 and the x are supplementary, so I know that x will be 40. Fantastic. And I know the exact same thing about the y and the 75. They are also what you may recall from an earlier chapter. They're same side interior angles. And angles, all thing angles, we'll be talking about in tomorrow's GeoPalooza. So if the phrase same side interior just kind of went right over your head, maybe you want to make sure to come to tomorrow's GeoPalooza as well. Okay, so y and 75 have to add up to 180, so that's why y is 105. One other thing about trapezoids, because trapezoids have two legs, if I have the midpoint of each of them and I connect them, I get a mid-segment. And the length of a mid-segment is the average of the bases. I have that there in the notes, but if you want to highlight it or underline it so that you don't lose track of where that is, think about what it means to take the average of two things. Taking the average of two things, that means you're adding them together and dividing by 2. Or adding things together and then taking 1/2 of it. So on that note, I can use that in order to solve for x in this trapezoid. So I know that x plus 3, the mid-segment, is the average of the bases. Now, myself personally, when I realize that inside the parentheses, when I combine my like terms and get 3x, I'm really not fond of the idea of taking half of that and trying to solve the equation from there. I would much rather get rid of that fraction, as you learned how to do last year in algebra. When you have a fraction that's kind of bogging the system down, remember you can multiply by the reciprocal in order to make that go away, or the least common denominator. So I'm multiplying by 2. And on the right-hand side of the equation, please understand what's going to happen when we do that. The 2 and the 1/2 cancel out, so you don't have to distribute that 2. The 2 that you do need to distribute is the one on the left side. Okay, so you end up with 2x plus 6 equal to 3x minus 2. It's an x. I just...
No, oh, okay.
Sorry. And then we just solve for x. Subtract 2x from both sides. I have x on the right-hand side. Add 2 to both sides, and I get 8. So x is 8. Depending on the instructions. In this particular problem, it doesn't specify, but thank you again for bringing that up. Read the question. Read the question, please. I'm sure at some point you had a friend that, maybe the algebra test last year, and they got a 398. You need a 399 in order to pass. How agonizing would it be?
Wait, for geometry?
I have no idea.
Oh,
I'm just saying, like, in previous testing systems, 399 was passing. How agonizing would it be if you got that 398 and you're like, I didn't plug that back in somewhere. What an agonizing point to lose. Okay, so read the question, take your time. Finally, the last kind of quadrilateral to talk about is a kite. And the definition of a kite is that it has 2 pairs of consecutive congruent sides.
Isn't the kite formula the same as the rhombus?
You're thinking area, and you're absolutely right. The formula for the area of a kite is 1/2 diagonal 1 times diagonal 2. Now that's not what I'm addressing here, but by all means, if that's something that had fallen out of your brain already, stuff it back in there, write it on your reference sheet. Area of a kite is 1/2 diagonal 1 times diagonal 2.
Oh.
Absolutely. Area of a kite equals 1/2 diagonal 1 times diagonal 2. It's the same exact formula for a rhombus. All right, so in this particular problem, we're just looking for angle measures here. A couple of things that you need to be aware of. The reason why, excellent segue, the reason why the formula for the area of a rhombus is the same as the area of a kite is because, remember how in a rhombus the diagonals are perpendicular? Same property exists in a kite. The diagonals of a kite are also perpendicular. So angle 1 right away is 90 degrees. Oh, that's... Okay, so angle 1 is 90 degrees, and then for angle 2, notice that angle BAD has been bisected, which means that angle 2 is congruent to this angle right next to it. So in this triangle here, what's the measure of this angle? I think I heard it. It's 50. 3 angles of a triangle add up to 180. So if that angle is 50, then the measure of angle 2 is also 50. I'll wait a second.
How did you get that?
Okay, once again, we noticed that angle 1 was 90 degrees.
Angle 1 is 90 degrees. Why is that 90 degrees?
Because the diagonals of a kite are perpendicular.
Alright.
Yeah, I mentioned that.
Oh, yeah. You got you.
Yeah. And then we have that triangle.
Mm-hmm.
angles of which add up to 180.
Alright.
And then the rest of what I have on that sheet is a little bit of practice for you to work through the problems, by all means, together if you need to, or if you want to, however you choose, for the remainder of our time together this afternoon.
Will you be recording tomorrow?
I don't know. But I am